This question is from the GATE Physics paper 2021. This is a numerical answer type, that is NAT, having 2 marks. The topic of the question is solid state physics. Specifically, this question is from the chapter Magnetic Properties of Material. The question is, consider an atomic gas with number density n equals to 10 to the power 20 per meter cube in the ground state of the atom at temperature 300 Kelvin. The valence electronic configuration of atoms is F7. So this means the last partially filled orbital is F, and that orbital, F orbital, contains 7 electrons. The paramagnetic susceptibility of the gas chi equals to m times 10 to the power minus 11. The value of m rounded off to 2 decimal places is, so basically we have to find the value of m which should be rounded off to 2 decimal places. There are some important informations are given which is required to solve this problem. The informations are: magnetic permeability of free space mu naught equals to 4 pi times 10 to the power minus 7 Henry per meter. The Bohr magneton mu B value is 9.274 times 10 to the power minus 24 ampere meter square. So basically the Bohr magneton is the magnetic moment of the elementary charge, that is electron, which occurs due to the spin or orbital angular momentum of that electron. And Boltzmann constant Kb equals to 1.3807 times 10 to the power minus 23 joule per Kelvin. So these informations we have to use to solve this question. So let us see how to solve this problem. According to the quantum theory of paramagnetism, we have the paramagnetic susceptibility chi equals to mu naught times n times mu j square by 3 kBt. Here mu naught is the magnetic permeability of free space. Kb is the Boltzmann constant, n is the number density of atoms, mu j is the effective magnetic moment of atoms. Here mu j can be written as Gj times root over j times j plus 1 times mu b, where Gj is the Landis G factor, J is given by L plus S, which is total angular momentum of the atom, and in our question some informations are given already. N, that is the number density of atoms, is 10 to the power 20 per meter cube. Temperature of the system T equals to 300 Kelvin. The valence electronic configuration of the atoms is F7. According to our question, the atomic system has the valence electronic state F7. Now we'll see how can we accommodate the 7 electrons in the F subshell or F orbital. For F orbital or the F subshell, we know the L value, that is the orbital angular quantum number or the azimuthal quantum number, L equals to 3. For L equals to 3, we know we can have ml values from plus 3 to minus 3. So we'll have 7 ml values. So basically there are 7 electronic states in the F subshell or the F orbital. So for these 7 electronic states, we can accommodate these 7 electrons in such a way each electronic state will contain one single electron. So as you can see from this configuration of the F orbital, the ml equals to plus 3 will contain one upspin electron, and correspondingly all the other electronic states will contain a single electron with upspin. So for this configuration of the electrons in the F orbital, we will have total spin quantum number S equals to summation over all ms, that is the spin quantum number of the electron, that will be 7 times 1 by 2, that is 7 by 2. But total orbital quantum number L equals to summation over all magnetic quantum number ml. So as this is half filled, so the summation of all ml will be 0 here. Now total angular momentum quantum number J equals to L plus S. So here S value is 7 by 2 and L value is 0 for this system. So this summation will give J equals to 7 by 2. So for the atomic system or atomic gas, the total angular quantum number J equals to 7 by 2. Now the spectroscopic term for the atoms with valence electronic configuration F7 is given by 8s7 by 2. This spectroscopic term is generally represented in the form of 2s plus 1 Lj. In our case, the S value is 7 by 2. So this 2s plus 1 will give 8. Now the L value, that is the total orbital angular quantum number, L equals to 0. For this we are having here x, and the total angular momentum quantum number is 7 by 2, that is J equals to 7 by 2. So we'll have here 7 by 2. Now the Landesi factor is defined as Gj equals to 1 plus J into J plus 1 plus S times S plus 1 minus L times L plus 1 divided by 2J multiplied with J plus 1. So we have for our system S equals to 7 by 2, L equals to 0 and J equals to 7 by 2. So we'll put this S value, L value and J value in this formula of the Landesi factor. So we'll have the Landesi factor Gj equals to 1 plus 7 by 2 times 7 by 2 plus 1 plus 7 by 2 times 7 by 2 plus 1 minus 0, as here L equals to 0, divided by 2j times j plus 1, here j equals to 7 by 2. So we will have here in the denominator 2 times 7 by 2 times 7 by 2 plus 1. Now if we calculate this, we will get the Landesi factor for our system Gj equals to 2. Now we will calculate the effective magnetic moment per atom. The effective magnetic moment per atom is given by mu j, which is given by this formula, that is mu j equals to Gj times root over j times j plus 1 times mu b. Here Gj is the Landesi factor of the atom, J is the total angular momentum quantum number of the system, mu b is the Bohr magneton. We have already calculated the Gj and J value for our system. The Landesi factor Gj is 2 as per our calculation, and J value is the 7 by 2. So we'll put the values here. So we'll get 2 times root over 7 by 2 times 7 by 2 plus 1 and mu b. Now mu b is given already in the question, that is 9.274 times 10 to the power minus 24 amps meter square. So if we calculate this, then we will get mu j equals to root over 63 for this this two term, 2 times root over 7 by 2 times 7 by 2 plus 1 times mu b. So mu b will put the value. So we'll get root over 63 times 9.274 times 10 to the power minus 24 amps meter square. Now the parametric susceptibility from the quantum theory is given by chi para equals to mu naught in mu j square divided by 3 kBt. So we have already calculated the mu j value, it is given here, and from the question we know mu naught value, in value, and the temperature of the system is 300 Kelvin, and Kb is the Boltzmann constant that we already know from the question. So we'll put all the values here. Then we will get chi para equals to 4 pi times 10 to the power minus 7, that is the mu naught value. In value is 10 to the power 20, and mu j squared is the this root over 63 times 9.274 times 10 to the power minus 24 whole square divided by 3 kb. Kb value is 1.3807 times 10 to the power minus 23 times temperature value of the system, that is 300 Kelvin. So after putting this, if we calculate this, we will get chi para equals to approximately 5.48 times 10 to the power minus 11. So we have to find the value of m, which is actually here 5.48. So the value of the m, as it has been asked in the question, that is 5.48. So we have already solved this problem in details, and we found that the value of m in the parametric susceptibility of the gas chi equals to m times 10 to the minus 11 is 5.48, which is rounded off to 2 decimal places.